Now, what I can do is that I can actually take this paper, separate it, and quickly basically freeze it. Okay, so I have suppose a mixture of 1 plus 2. Okay, and then I'm heating it up. At that temperature, some temperature will be reached, okay, where actually boiling starts. But remember that this boiling temperature is fixed by the composition, initial composition. Okay. Now initial composition, as I said, that suppose this is 0.3 for 1. Okay. Now once I reach 0.3, I see the vapor comes out. Okay. But if I can actually collect this vapor, okay, and then cool it, make a solution, what will happen? So basically I can actually cool it, make a liquid, but this liquid, look, now it has a composition of 0.7. So it is enriched. Right? Then I can repeat the process once again. I collect it first. Okay. Then I again heat it up. If I heat it up for 0.7 mole fraction, this is the boiling point. Again, it will basically, it will be a horizontal line. Okay. Something like that. Okay. And then I can again cool it down. Okay. So every cycle I'm doing it. What I'm doing is basically I'm enriching the amount of 1. You can think in terms of 2 also. Okay. So whichever is the more volatile, I'm actually collecting it more and more. So what I'm doing is known as, all of you know, fractional distillation. Right. Now there is an interesting thing. How many steps I did it? It will depend on 2 things. One is that what I started with. Okay. Like I could have started with a composition which is here. So then actually it will be something like here, right? So it will first go here, then it will come here, then it will go here, it will go here. That is one thing. But if I start from a fixed thing, okay, I see it will be dependent on how these 2 curves are related to each other. Okay. Meaning, what I am trying to say, for example, this is say for some particular 1 and some particular 2. Okay. Gives you this kind of like boiling point, okay, but I could have actually some 2 liquids, 1 and 2, different 1 and 2, okay, for which I could have actually the curves which are much closer, okay, but then what will happen? Then suppose I am just doing the same thing. I am starting from some temperature, boiling, okay, at this point actually it just fractionates here. Okay. Then I am cooling it down, collecting it, again heating it up. Okay, at this point it is fractionating. Okay. Again I am cooling it down. Okay. Now you see the number of steps are increasing. Okay. So it will depend actually how wide is this liquid vapor equilibrium region is. Okay. If it is too narrow, means actually the liquid and the vapor are very close by, then I need to actually increase the number of cycles or number of steps, basically, not cycle. Okay, I have to basically do it, collect it. So every step I am enriching little and little. Okay, but if this region is too wide, okay, within few steps I can actually probably enrich 99%. Clear? So fractional distillation will always depend. So basically the phase diagram has all the information. Okay, of fractional distillation. Now, sometimes what we just said so far, okay, is for actually ideal solution. We have not discussed about non-ideality, how to describe, but I will give you an example. What happens if this situation is non-ideal? Okay. Now, non-ideal in the sense that now there are very specific interactions, okay, between the molecules. Now, what can happen is that suppose I am increasing the temperature. Okay, here the A and B, they are not basically interacting with each other. Okay, now suppose there is some interaction. Now the interaction may be favorable, it may be disfavorable. In the sense, what is favorable interaction? Favorable is suppose I put some acid in water. Okay, say some carboxylic acid and water, both are volatile suppose. Okay, but then what happens is that they have hydrogen bonded. They are hydrogen bonded together, right? So it is very difficult to actually separate them. Because everything, if you remember, okay, where we started from, actually our original model is Gibbs free energy, right? Now in the Gibbs free energy model, what we wrote? It came from dg is minus sdt plus vdp plus mu I dni, right? And this mu I dni actually is related to the Gibbs free energy of mixing, because we show it, right? I mean, like you can always show it that RTLN xi, right? Summation over that. That is basically the Gibbs free energy of mixing if there is no interaction. But if actually there is additional interaction, right? So the Gibbs free energy of mixing will be more negative if it is more attractive. It can be actually more than that, more than the ideal, because if they are repulsive, suppose, like oil and water, okay, they do not mix together, hydrophobic interaction, okay. Now again, when I say hydrophobic, there is nothing called repelling interaction, which means the water molecules and interaction between the water molecules are much more, or interaction between the same type of molecules are much more than the interaction of different type of molecules. That's why you see an overall repelling effect. There is nothing called a repelling effect, okay, because everything is a van der Waals force. And if you think in terms of a dispersive interaction, that is an attractive force, right? Now then where the repulsion is coming from? Repulsion is coming because actually oil likes oil and water likes water. Okay, but it does not mean oil doesn't like water. Okay, the liking between the water and the liking between the oil is more than the liking between oil and water. That's why they separate out. Okay, so now the question is, if those kind of interactions are present, then there will be no mixing effect. Okay, so like from the ideal reduct, if they behave ideally, just no interaction, and like we showed it, like for an ideal gas, we start from same pressure and then there is a Gibbs free energy of mixing, right? So then the interaction will be slightly higher also. Okay, so then we can have basically two kind of extreme regimes. Okay, so this is the ideal thing when actually we have basically no interaction present. Okay, now the question is how it will look like for a two component system if there is some interaction which is present. Okay, and how the ideal curve looks like. Okay, let us just try to draw it first. Again, it's the same curve. Okay, so it's temperature versus mole fraction. Okay, now in an ideal case, okay, so it is a similar curve. Ideal case, actually I should have something like this, right? Now think about it. If there is if there is an attractive interaction, okay, what should happen? Like suppose at this composition I am increasing the temperature. Okay, if it is ideal, when this temperature will reach, okay, it should boil, right? But if there is any attraction, meaning suppose, just think a very simple thing, like just take two things like water and something else which is miscible in water. Okay, but suppose there is no interaction, and then what I'm saying here, if I'm increasing the temperature, okay, so at this point basically the water molecule is leaving the other component. Okay, but if it doesn't leave, what should happen? Then this boiling temperature should be high because they are now attracted together. Okay, you are heating it up, but they're still not like going out. Okay, so which means this curve actually will lie higher. Okay, and in some very extreme case, what you can have is that this curve actually looks like this. Okay, meaning think about it, this composition. I'm actually increasing, but what I see here is that the liquid actually, okay, is basically there is no liquid vapor equilibrium region, but the liquid and vapor at this temperature has the same composition. Okay, these two curves are touching. At this temperature, at this composition, we call it as an azeotrope as form. Okay, but what is the meaning of azeotrope? Okay, let's just try to think about it in this way. Suppose I start from here. Okay, right side of the isotope. Meaning, suppose I had some composition of some liquid, okay, and then I'm just trying to boil it. Now look at it. This part looks like something like that. That's why I'm starting from here. Okay. And then what I'm doing is that I'm just boiling the mixture. Okay. And then what will happen? So the vapor will basically come out, which is enriched in one component one. Okay. But suppose I'm removing the vapor. If I remove the vapor, an interesting thing will happen. What will happen? At this point, if I remove the vapor, okay, so remember all these phase diagrams, we are whenever we are drawing, the total number n is fixed, right? But removing the vapor means actually I have removed some amount. But what I removed? Actually, I removed more of one, right? So what is left behind will be somewhere here, left to it. Clear? Because at this composition, this was the vapor. Liquid composition. One's liquid composition, and this is one components on. But this one, suppose I am removing. Okay. So then this guy is actually enriched. Okay. The one is enriched, and actually, the 2 is enriched. Basically. Okay. Because I am showing the one thing. Okay. Which means the mole fraction which was present in the solution for 1 should decrease. Okay. I have not changed the temperature, so I basically have to start from here then. Temperature is set. Still I am heating. What will happen? Again it will go like this. Okay. Again some vapor is coming, and I have made an arrangement where actually I am sucking out all the vapor. Okay. So what is left behind? Okay. Should have a less composition, something like that. Okay. So then every time if I keep on increasing the temperature, okay, I will see at point will reach where actually this liquid and the vapor, okay, they are basically have the same composition. Okay. Which means now actually there is no enrichment or something like that. Okay. So at that temperature, okay, the boiling or basically the liquid vapor equilibrium region, okay, for that composition, okay. So what is happening is that both of them are actually boiling together, 1 and 2. Okay. So how do you interpret it? Like suppose if I start it here again, I have an enrichment in the vapor. Here I have an enrichment, but here I don't have any enrichment. Okay, which means if I suppose if this is just take some number, let's say 0.3. So if I had basically was boiling say component 1, 2 is enriched. Okay. Suppose I started with, let's say this is 0.6. I started with the mixture where I had 60% 1, 40% 2. Okay. And I boiled it. Okay. And in the boiling mixture, 1 is more volatile. Okay. That is sucked out. So 2 is getting enriched. Or in other words, 1 is getting basically decreased. Okay. And then I reach a point where actually I have 0.3 or 30% of A, 30% of 1, component 1. At that point, if I boil it, then I see that there is no enrichment because these two curves are basically together. Which means if I heat the 30% of say water and something glycerol, okay, in the vapor also it will come as 30% water glycerol. Clear? Now the x1 and y1 concept is this kind of same. Okay, because that was y1, that was x1. Okay, so meaning I have to get a particular combination. Okay, where I boil for these two mixture. Okay, that composition will not change. So this composition, if I start with, I will never ever be able to distill because there is no enrichment. Okay, you will just keep on going into the vapor phase straight. Yeah, it's the same thing. Okay. Now, which means actually for a particular mixer, I have an example here. Like the example is hydrochloric acid and water. Actually, yeah. This is just a practical example. HCl water mixture. for 80% water's mole fraction, which means actually when XH2 is basically 0.8. If I start with that, okay, then you can show that. Then of course you can see that on this isotope actually, okay, I have a fixed temperature also, boiling temperature, but that won't be 100 degrees centigrade because 100 degrees centigrade is for pure water. Okay, it is slightly more. It is something like 108 degrees centigrade. Okay, if I just boil it there, I will see that 80% is always maintained. 80% means actually 20% is also maintained. So their relative composition in the liquid phase as well as the vapor phase is the same. Clear? Okay. But this is for something where actually I said that the attraction is favorable. Why? Because I said that look, this was the ideal curve, something like that. Okay. But the liquid actually I have to increase the temperature more to boil. Okay. It could have the other way. Okay. So the other way, how it will look like? It will be something like this. Okay. So here actually it is the other way, as you can see. Okay. Other way means actually it is kind of boiling, okay, at a lower temperature. So this is called high boiling azeotrope, where you have component 1 and 2, okay, have a favorable attraction. Now when I say favorable, it is more favorable compared with the Gibbs free energy mixing for ideal component. There will be always a negative thing. If I have A and if I have B, they are more like the negative free energy will happen when A and B are completely mixed. Okay, but that's just mixing without any interaction. Okay, that is the Gibbs free energy mixing. Minus XIL and RTL and XIL and XI, something like that. Okay. In addition to that, okay, if I now have favorable interaction, then the boiling is basically high. But if I have unfavorable interaction, okay, so then the boiling will be at a lower thing. But the explanation is the same, right? So like this here actually I am doing the enrichment thing. Okay. Here it will be interesting if you actually look at from component 1. If I start from here, okay, then I'll enrich, and at this point once I reach it, okay, I cannot enrich more. Clear? Okay. So once I reach that composition temperature, okay, I cannot enrich more. Okay. Here enriching means I'm actually starting from the left side. Okay. And then basically if I keep on hitting it, the same composition will also come into the left. Okay. So this is again a real life example. That's why the curves are so different. But now the next question is how we can model the real life thing. Meaning, instead of like, what is the concept of activity? That will start in tomorrow's class. Okay. But let me quickly summarize this part. Okay. So what we did is that, because this part is mostly very much conceptual thing. Okay. Now we said that, okay, fine. First thing first, we showed you how the phase rule comes. What are the number of degrees of freedom? And that we said that that is basically the total number of degrees of freedom which can be interdeleted. Okay. And that is given by the number of equations. Right? Because any equation gives a constant. And then you can further make a constant like we did here. Pressure is fixed. In all this case, we have P fixed. Okay. And then we talked about our like most familiar phase diagram, which is the pressure temperature phase diagram. But then we asked the question that if I have actually multiple components, right, then I can actually play with the mole fraction of the components independently in each phase. Okay. And then I will have a more number of degrees of freedom, and which I usually cannot plot. Right? But what I am doing here is that I can cleverly plot it if I make one more constant, like temperature constant. In the earlier case I showed, right? then I plot only from the solution's perspective or like vapor's perspective. By the way, when I wrote like x1 and y1 kind of thing, right? Actually, there are two variables. One axis is x1, one axis is y1, but I am just plotting it together. Okay, these are there are three things there. Okay, remember that f was basically like if I calculate the total thing, right? So I can write it the x1, I can write the y1 also. Okay, but then the question is x1 and y1 are related. Okay, so ultimately the f will be 2, right? Because we established a relationship. But all this interesting thing happened because the vapor pressure of the two liquids were not identical, which means one is more volatile than the other. And if that happens, I'll have a very interesting variation of the vapor pressure, okay, with the total pressure, right? And then I can connect that vapor pressure with mole fraction in the vapor phase. So we have to be very careful whether we are saying the mole fraction in the liquid phase or in mole fraction in the vapor phase. Okay, because the behavior will be slightly different. And then it showed that if I actually increase the pressure, okay, I can actually think about a vapor condensing, or if I decrease the pressure, keeping the fixed composition of the overall thing, okay, I can always think about like there is a like condensation, a phase transition is happening. However, the composition will not be same. Why? Because as it is just crossing a region, which is a liquid vapor equilibrium region, okay, then the total composition doesn't matter. Because you are entering a region where like x1 was the more like x1 was the variable, and then you are going to y1. But the x1 and the y1 will not be the same if I just increase the pressure or temperature. It can be same only in case of isotopes. Okay. But actually the liquid and the vapor curve are coinciding, which means if I draw a vertical line, right, then I see that the composition is fixed for that particular temperature. Otherwise, it will never. Otherwise, it will always enrich one phase versus the other. Okay, the way we wrote it, as if that one is getting enriched. If one is getting enriched, you can always think that in the solution, I'll have more and more 2, or 1 is basically decreasing. Okay, and we showed very interesting consequence that if I keep on doing it, I won't be able to actually fractionally distill it, okay, after a certain temperature, okay, and composition, of course. And if that is reached, then I cannot do anything, because if I just keep on doing it, the entire solution will come into the vapor without changing the composition. Clear? Alright.